In this video, we are going to explore what is meant by metamaterial absorbers and what is its importance compared to the classical absorbers and how these structures are achieving the absorptions. Let's see. Let's start with an absorber principle. Consider a structure. When a wave is incidentally on it, based on the property of this structure, some part will be reflected, some part will be absorbed, and some part will be transmitted. So if we consider the incident wave as 1, we can see that this absorption will be equal to 1 minus T minus R. So that will be the absorption. So let's assume if our structure is backed by the metallic plate, then absorption will be equal to 1 minus R because this metallic plate will not anything to be get transmitted. So in that case, we can give the absorption as 1 minus R. This means that if we have to get a perfect absorber, there must not be any reflection. That means all the incident wave has to be absorbed here. So let's see how we can achieve no reflection. That means if this is the equivalent circuit of a structure, that means this is the impedance of our structure, and this is the grounded metallic plate, and the total impedance offered by this structure is Zin, and Z0 is the free space impedance. Then the total reflections can be given by Zin minus Z0 by Zin plus Z0. So this is the basic equation for the reflectivity. That means that for the reflections to be 0, Zin has to be equal to Z0. So if that occurs, then the reflections will become 0. So we have to design a structure such that the total impedance offered by the structure should be equal to the free space impedance. Then the reflections will become 0. Now we know that how we can achieve no reflection case, and we have to make sure that all the things are getting absorbed. If it has to get absorbed, this structure has to be lossy. If the structure has lossy, all the things will be get absorbed. So while designing an absorber, the main things to be considered is we have to make sure that there is no reflection, and the material that we are going to consider is lossy structures. So these are some of the commonly available classical absorbers like Salisbury screen, German absorber, Dallenbach layers, and the carbon-loaded geometric transition absorber. All are aware about these type of transition absorber. We are using these absorbers widely in anechoic chambers. So when we see all these absorbers, we can see that the thickness of the structures is comparable to the quarter wavelength. That means all these classical absorbers are characterized by large thickness. If you want to know more about these classical absorbers, you can watch our video. I will put the link in subscription. So we have seen that for an absorber to be act as a perfect absorber, the impedance should be matched to the free space impedance and the structure should be lossy. So let's see what is mean by metamaterial absorbers and what are its important compared to the classical absorbers. We know that metamaterials are periodic array of patches over the grounded dielectric. So one of the condition of the absorber is the metamaterial impedance, that is the structure impedance to be matched to the free space impedance. So the structure of metamaterial, like we can manipulate the size, shape, and dimension of these patches so that the impedance of the structure to be matched to that of free space. So that means we can achieve the first condition, that is the impedance matching, by manipulating the patches and dimension of the dielectric and everything, so that we can make sure that the input impedance of the structure is matched to the free space impedance and the reflection can be make 0. And the next condition is the structure has to be like lossy structures. So we know that metamaterial consists of patches over the grounded dielectric. So that means it has two layers like array of patches and the grounded dielectric slab. So there is two options to impart losses onto the structure. We can either impart losses onto the dielectric. So if we uh, provide losses to the dielectric, we will get ultra narrow band absorption, and we will call it as the perfect metamaterial absorber. Otherwise, if we are providing losses to these patches, so how we can provide losses to the patches? We can put resistors in patches, or using the resistive inks, we can provide losses to the patches. So if we provide losses to the patches, we can get wideband absorbers, and these type of absorbers are called circuit analog absorber. So in case of metamaterial absorber, uh, they are way better compared to the classical absorber because they provide low profile polarization insensitive and angular stable structures for absorption. Let's go into some more details. First, I'm considering a metamaterial absorber. So I'm considering this periodic array of these type of square loops on a grounded dielectric slab. So in this slide, we are going to see how this dielectric loss is affecting the absorption. So here I have considered the loss in the substrate from 0 to 0.22. So when I am considering a lossless substrate, you can see that this is the reflection coefficient. That is, the red one is the reflection coefficient. You can see that how the impedance is here. You can see the impedance is around 3000. We know that impedance of the free space is 377, but this structure is providing an impedance of 3000, which is way greater than the impedance of the free space. So we can see that all are getting reflected. And next I'm going to increase the loss. So when I increase the loss in the dielectric, you can see that that is the blue one. Blue one shows that the impedance of the structure. So this is the impedance of the structure. You can see here that impedance of the structure is reduced to 377 ohm, and this shows that there is no reflection, and all the whatever is incidenting, it is getting absorbed. And the third one, I'm just increasing the dielectric loss again. So when I increase the dielectric loss again, it shows that the real part of impedance is becoming zero. That means that it is behaving like a perfect electric conductor. That is, there is no absorption. So we have to carefully choose the loss in the dielectric to get the perfect absorbers. And this is a power loss density distribution graph. Here you can see that at the resonant frequency, all the powers are getting loose in the dielectric. So the metamaterial absorber used the dielectric loss for the perfect absorption. And next is the circuit analog absorber. In this case, we can use the resistors or resistive ink to provide the resistance to the patch. The main characteristics of this circuit absorber is, here you can see that the absorption is offered in a very high band of frequency ranges. You can see from 5 to around 20, it is providing the absorption of around 90%. So this is the fabricated structure. Here you can see that the resistors are embedded on these structures. And here, this is the power loss distribution. Here you can see that power loss is mainly concentrated on these resistive patches. Okay, that's all regarding this. I hope you understand the concept of metamaterial absorbers and circuit analog absorbers. Thank you.